Ever glance up at the night sky
Yeah.
and, get that feeling of, how does any of that even work?
Yeah.
Get ready, because today's deep dive is all about some seriously mind-bending physics
It really is.
happening right before your eyes, even if you need some, seriously powerful telescopes to see it.
What's so cool about this topic is we're not just talking about, like, abstract theories. It's like we're diving into how relativity, the very fabric of space-time, literally shapes the light we see from these distant objects.
We're tackling a chapter from one of the greats for this one.
Oh, yeah.
Richard Feynman, his Lectures on Physics, to be precise.
Classic.
Volume 1, Chapter 34, if you want to follow along at home.
Nice.
And don't worry, even if relativistic effects in radiation sounds a bit like something out of Star Trek,
Right.
Feynman was famous for making even the wildest physics surprisingly understandable.
He really had a knack for, like, getting to the heart of things, you know? And what we're getting at here is how the simple act of something being in motion completely changes how we perceive its light, especially when that something is moving at, well, near light speed.
All right, I'm already hooked. But before we launch into warp speed, maybe we should ground ourselves a bit.
Yeah.
So we're talking about light from, say, a charged particle like an electron.
Yeah.
And how that electron's motion affects what we actually observe.
You got it. Think of it like this. A charged particle, just by existing, creates these invisible force fields around it. We call them electric and magnetic fields.
Okay.
You can almost imagine them as this sort of aura surrounding the particle.
Okay, I'm picturing it. So how do these auras play into the whole light speed equation?
Well, here's where it gets really wild, right?
Yeah, okay.
Imagine you're on a train and you're shining a flashlight towards the front.
Okay.
To you, the light's moving at the speed of light. Yeah.
Right.
But to someone standing on the platform watching you go by, the light is moving at the speed of light plus the speed of the train.
Whoa. So the speed of light stays the same, but it's like reality adjusts around it or something.
Kind of, yeah. It's not that simple, but you're getting the idea.
So what happens to the light from our super-fast electron? Does it somehow travel faster than light?
That's the catch. It can't.
Right.
The speed of light is the ultimate speed limit. Nothing can go faster. But that doesn't mean things don't get strange when you're moving close to it. And this is where understanding how we perceive events and the light from those events becomes crucial.
Okay, so we're talking about perspective again.
We are.
How do we even begin to wrap our heads around light emitted by something moving at near light speed? It's not like we could just chase after it and check.
Right, we can't. But Feynman, he had this brilliant way of visualizing this.
Okay.
He talks about translating the motion of the charge backwards at the speed of light.
Okay.
It's
Rewinding.
Yeah, like hitting rewind, but at light speed. To figure out where the charge appears to be at the moment its light should reach us, it's that apparent position that determines how we see its electric and magnetic fields, and thus the light itself.
That's such a cool trick. It's like we're rewinding the universe itself to understand how the light from this speeding electron reaches us. It's making my brain do backflips, but in a good way.
And this mind-bending concept, that's just the tip of the iceberg. When we start talking about things like synchrotron radiation, it's this understanding of perspective, of rewinding light, that lets us make sense of the amazing things we see happening, not just in, particle accelerators here on Earth.
Oh, wow.
But also out in the universe on a scale that's almost impossible to grasp.
Wait, are you telling me we can actually see relativity in action?
Oh, yeah.
Now you've really got my attention.
Oh, absolutely. And it all comes down to this phenomenon we're about to unpack, synchrotron radiation.
Okay.
It's happening, in these massive machines we've built here on Earth.
Right.
But also out in the universe on a scale that's almost impossible to grasp,
Okay, synchrotron radiation.
Mm-hmm.
It sounds like something out of a superhero movie. Break it down for me. What exactly are we dealing with here?
It's actually not as complicated as it sounds.
Okay.
Essentially, it's the light emitted by charged particles, usually electrons,
Right.
that are,
Zipping around.
Yeah, zipping around super fast in a magnetic field. Imagine these tiny electrons, right, doing laps in a magnetic racetrack at close to the speed of light.
A magnetic racetrack. I like it. But why do they emit light in the first place? What's the magnetic field got to do with it?
Yeah, That's a key part of the puzzle.
Okay.
So you see, a charged particle moving through a magnetic field experiences a force.
Right.
But here's the thing. That force isn't pushing the electron forward.
Okay.
It acts at a right angle to its motion, so...
Okay, so instead of speeding up, it's like the magnetic field is constantly nudging the electron to the side.
Exactly. And that constant sideways nudge, right, forces the electron to travel in a circle.
Okay.
The faster the electron goes and the stronger the magnetic field, the tighter that circle becomes. And we're talking some serious forces at play here.
So we've got these electrons doing high-speed donuts in a magnetic field. But how does that translate into the light, the synchrotron radiation that we're actually observing?
Well, anytime a charged particle is accelerated, and moving in a circle is a form of acceleration.
Right.
It emits radiation. We see this even with, slower moving charges. Think about how a radio antenna works. But here's where things get really interesting.
Let me guess. It's all about those near light speeds again. Does the light, break the cosmic speed limit?
It's tempting to think that.
Yeah.
But it doesn't.
Okay.
Instead, something even weirder happens.
Okay.
Remember that rewinding trick Feynman uses to figure out how we perceive light from a moving source?
Oh, yeah, like hitting rewind at warp speed to see where the electron appears to be when its light reaches us.
Precisely. When you apply that concept to synchrotron radiation and factor in those incredible speeds, something remarkable occurs.
Okay.
Instead of, the typical radio waves you might expect from, a circling electron, the emitted radiation gets dramatically compressed.
Compressed, like squeezing a balloon. What does that actually do to the light itself?
It completely changes its properties. The wavelengths of the light gets shorter, and its energy increases dramatically. Instead of radio waves, we suddenly have X-rays, which are, thousands of times more energetic.
Wow. So even though the electrons aren't breaking the speed limit, the light they emit gets this incredible energy boost thanks to relativity.
That's pretty wild.
Yeah.
But it also makes me wonder if we can create this kind of radiation here on Earth in our, fancy synchrotrons.
Right.
Could it also be happening naturally, out in space?
You're right on the money. And one of the most spectacular examples of naturally occurring synchrotron radiation is the Crab Nebula.
The Crab Nebula, that name rings a bell. Isn't that,
Yeah.
incredibly old, astronomically speaking? It is. We're talking, nearly 1,000 years old. Chinese and Japanese astronomers recorded seeing a guest star in the sky back in 1054 AD.
Wow.
What they were witnessing was actually a supernova, a massive star exploding at the end of its life. And the Crab Nebula, that's what remains of that cataclysmic event.
Okay, so we've got this supernova remnant, the Crab Nebula.
Yeah.
How do we know synchrotron radiation is involved? What makes it stand out from just any other nebula out there?
That's where things get really interesting, visually. If you look at an image of the Crab Nebula,
Yeah.
a few things stand out. You've got these intricate red filaments, which come from excited gas that's pretty common for nebulas.
Okay.
But then there's this central fuzzy patch of light that's different.
Different how? Is it just reflecting starlight? What makes it special?
It's not reflecting light, it's emitting its own light across a continuous spectrum,
Oh, wow.
like a rainbow.
Okay.
That tells us it's not just coming from, specific elements, there's something else going on there.
Okay, so we've got this mysterious glow. How do we know it's synchrotron radiation for sure? Is there a cosmic fingerprint we can look for?
There is, and it has to do with something called polarized light.
Okay.
Think about how polarized sunglasses reduce glare.
Right.
They only let light through that's, vibrating in a specific direction.
Right, so polarized light is kind of organized light,
Yeah.
all vibrating the same way.
Exactly.
But how does that connect to the Crab Nebula and our, speedy electrons?
Well, when astronomers observed the Crab Nebula using polarized light, they found something incredible.
What?
The nebula's brightness changed in distinct patterns depending on the orientation of the polarization filter.
Wait, so the way the nebula looks changes depending on how we're filtering the light. That's bizarre.
Exactly. And these patterns, these changes in brightness, are a clear sign that the light we're seeing is being emitted by charged particles spiraling around in a strong, organized magnetic field.
So we're seeing light from electrons that have been doing high-speed donuts in this nebula's magnetic field for almost 1,000 years. That's kind of mind-blowing.
It really is, and it highlights just how powerful and long-lasting the effects of synchrotron radiation can be. But there's another fascinating wrinkle to this story.
There's more. Hit me with it.
Yeah.
Okay, my brain is still trying to process the fact that we're, seeing light from electrons that have been spiraling around for 1,000 years. It's What's the secret sauce? How do they stay energized for so long?
That's the million-dollar question. It's one of the mysteries surrounding the Crab Nebula that astrophysicists are still trying to, you know, fully crack. It's a good reminder that even when we think we're starting to understand these cosmic processes, the universe always has a few more surprises up its sleeve.
I love that there's always more to discover. But speaking of discoveries,
Yeah.
I think our deep dive into Feynman's work, revealed a few more relativistic effects we should at least touch on before we wrap up here. We briefly skimmed over something called Bremsstrahlung, which sounds like,
Mhm.
well, I'm not even going to try to pronounce it.
Uh-huh.
What's the layman's explanation for this one?
You're not alone. It is a mouthful.
It really is.
But the concept is actually pretty straightforward. Imagine our, super fast electron again.
Okay.
But this time, instead of like smoothly curving in a magnetic field, it has a close encounter with an atom.
Oh, so it's like an electron fender bender. Does it throw off sparks?
In a way, yes. You see, the nucleus of an atom has a positive charge and opposites attract.
Right.
So when the electron zips by, that positive charge gives it a sudden yank.
So it's like a cosmic game of tug of war, throwing the electron off course. And since it's accelerating, does that mean it's emitting radiation?
You got it. And because we're talking about incredibly fast electrons to begin with, this braking radiation, which is what Bremsstrahlung essentially means, can be incredibly energetic. We're talking X-rays, even gamma rays, which are even more powerful.
Hold on, gamma rays. Those are the ones we use in, like, superhero movies to give people superpowers, right?
Well, not exactly, but you're not far off.
Okay.
Gamma rays are the most energetic form of light. And they're, often produced in these extremely high energy events, like those happening in the centers of galaxies.
Right.
Or, as Feynman explains, when you slam the brakes on an electron going near the speed of light.
So it's like the sudden deceleration unleashes a burst of incredibly powerful radiation. And we can actually use this, right? I vaguely remember something about synchrotrons being involved.
You're right. Synchrotrons aren't just for studying high-speed electrons. They can also generate these high-energy photons.
All right.
Gamma rays included, through Bremsstrahlung.
Okay, so we speed up electrons to near light speed, we make them slam on their cosmic brakes, and boom, gamma rays. What do we do with them, besides, potentially creating superheroes?
Well, we'll leave the superhero creation to the comic books for now, but scientists use these gamma rays for all sorts of fascinating research, from studying the structure of materials at the atomic level to, developing new medical imaging techniques.
It's amazing how these mind-bending physics concepts have such tangible applications in our world. But before we run out of time, we have to touch on one more thing. Something we often experience with sound, but also happens with light. The Doppler effect.
It's a classic, and Feynman doesn't disappoint in his explanation.
Right.
To recap, the Doppler effect is why an ambulance siren sounds higher pitched as it approaches you,
Right.
and lower pitched as it moves away.
Right. It's like the sound waves themselves are getting, squished or stretched depending on the motion. But how does that work with light?
The principle is the same. With light, it's the frequency or color that changes based on the relative motion between the light source and the observer. Light from a source moving towards us gets compressed to higher frequencies, shifting towards the blue end of the spectrum. If the source is moving away, the light is stretched to lower frequencies, shifting towards red.
So if we're looking at a distant star and its light seems a bit redder than it should be,
Right.
that could mean it's moving away from us.
Yeah,
And if it's blue shifted, it's coming towards us.
precisely. And just like he did with, the rewinding trick for synchrotron radiation, Feynman uses both, visual illustrations and mathematical equations to show us exactly how this Doppler shift works,
Right.
proving just how consistent and elegant the theory of relativity really is.
It's like the universe is speaking a language, and relativity is the key to understanding it. This whole deep dive has been incredible. But before we wrap up, there was one final point Feynman made that really caught my attention. Something about light having momentum. I always thought momentum was tied to mass, and light is, light.
You're right, it's a mind bender. We tend to think of light as this, intangible thing, but it turns out that even without mass, light carries momentum.
Oh, wait, so you're telling me that light, even though we can't feel it directly, is constantly pushing on things. That's wild.
It is. It all goes back to those electric and magnetic fields that are an inherent part of light.
Right.
These fields interact with charged particles, creating a tiny force that always acts in the direction the light is traveling.
Okay.
That force, that's light's momentum.
So even though that momentum is super tiny, It's still there,
Yeah.
constantly shaping the universe around us.
Exactly. And what's even more mind-blowing is that this momentum is directly related to light's energy. It's like this fundamental cosmic connection between energy, momentum, and the speed of light itself.
It's incredible to think that something as, like, seemingly simple as light can reveal such profound truths about the universe. We started with what seemed like a simple question: how does motion affect light? And we ended up down this rabbit hole of relativity, synchrotron radiation, gamma rays, and light having momentum.
Haha.
Yeah,
It's
it's quite a journey.
it really is.
It's a testament to Feynman's genius as a teacher that he could take such complex topics and make them not just understandable,
Right.
but downright fascinating.
Absolutely. He reminds us that physics isn't just like equations on a chalkboard. It's the story of how our universe works, from the smallest particles to the most distant galaxies. And sometimes that story can be even stranger and more wondrous than anything we could imagine.
And that's a pretty great note to end on, don't you think?
I think so. This has been awesome. Thanks for taking this deep dive with me.
Anytime.